Hi, my name is Sonia Chernova. I'm faculty at Georgia Tech. I'd like to thank the organizers of the workshop for having me come out and speak. With me today is my PhD student, Wei-Yu Liu, and together we're going to talk about going beyond the label, robots that reason about object semantics. And this work, much like many of our other projects, is driven by the question of how do we develop robust autonomous systems that operate in human environments. Today we have robots on Mars, we've had robots in factories for decades. We still don't have robots in our homes, in our offices, grocery stores, and so on. And the dynamic nature, diverse nature of these environments, the fact that every single home is entirely unique, presents a huge challenge for autonomy. There are a lot of different research problems within that, everything from perception to planning to reasoning. For today, I want to talk about a specific subset of the challenges or potential solutions to this problem, which have to do with semantic reasoning. How do we leverage semantic reasoning to achieve more robust autonomy, more robust modeling of the world, reasoning about objects, or interaction with people? So Wei-Yu and I are going to tag team throughout the presentation. We're going to cover 3 different projects related to semantic reasoning. And try to capture and hopefully convince you that semantic abstraction is really the way to go here. So to start things off, I'm going to just introduce the idea of semantic information and semantic reasoning to make sure we're all on the same page. First, here's an example from computer vision. This is an image from a recent workshop. It's handcrafted, as far as I know, but there's many examples similar to this that are automatically generated by different algorithms. Here, the input to the algorithm is an image of, in this case, 2 horses on a street pulling, with a carriage and 2 men. If you run object recognition, that's all you get are those labels. If you perform semantic analysis of the scene or obtain something called a semantic scene graph, then the information that you end up getting is richer and captures the underlying relationships between these entities. For example, here you'd say, that these horses are Clydesdales, they're pulling the carriage is green, and the men aren't just standing around, they're riding inside that carriage. And so now we're able to model the semantic relationship between all of these entities and have a much, much deeper understanding of what's going on in the scene than we did if we just captured the labels corresponding to the objects in the image. The same type of reasoning can be applied to other kinds of data. We could look at XY locations on a map and say, well, these ones are the hallway, and these other ones are a meeting room, and these other ones are an office. We could look at groupings of different pixels and how they form collections of surfaces or objects. Or we can drill down and look at specific objects and their parts. So we could say, here's a cooking pot and has a part for grasping, that's the handle, and then it has another part that's for containing other things. And so now that's a semantic model of that object that tells us the affordances of that object, what can be done with it. And so more generally, if we take all of these ideas and combine them across these different fields, what semantic information inevitably entails is a type of data abstraction, typically taking the form of word labels that represents concepts, facts, ideas, or beliefs about the world. And in turn, when we talk about semantic reasoning, what we're doing is drawing new insights based on inference over that semantic information. And often the reason we need to draw new insights is because when we perceive the world, we only see a small slice of the true reality. I might be able to see my kitchen, but if I want to make coffee, I might not immediately have a coffee pot or a cup in sight. I have to perform inference in order to locate those items, and so do robots. And so over the next couple of minutes, we're going to talk about ways in which semantic reasoning can be used to enable robots to reason more effectively about interaction with and models of different objects. And so with that, I'm going to turn it over to Wei-Yu.
Thank you, Sonia. Now I would like to show a specific type of semantic reasoning with an example before we dive into the projects. Shown on the left here are some facts in the form of triples that represent common sense knowledge about objects, such as a spoon is an utensil and a pen can be found in an office. Realistically, a robot will not know all the facts about the world. For example, we may ask the robot to find a fork, but the robot does not know where a fork is usually located. In this case, the robot needs to reason about these known facts to infer the missing information. Here, the robot will not be able to perform logical reasoning to infer the missing information, but it can leverage patterns in these known facts to make an informed guess. One line of reasoning is that objects that are in the same subtree of an entity hierarchy are likely to be found in the same place. For example, the spoon and the fork, they are both utensils, so maybe they can be found in the same place. Many relational machine learning techniques have been developed to leverage statistical patterns in the structured knowledge. One approach is to build a latent model consisting of embeddings that map each symbol to a vector, and a neural network that takes as input these input vectors representing a fact and outputs a score indicating whether the fact is true or not. After training the model on both true and false facts, the model can be used to infer new information. In this example, the model can be used to predict that a fork is more likely to be located in the kitchen. We build on this type of techniques to allow robots to consider a broader range of contexts for grasping and also develop a more accurate mental model of the world, capturing relations between multimodal object properties. We will first talk about how do we reason about environmental contexts for grasping. Many methods have been developed over the years to facilitate stable grasping of objects. However, stability is only the first step towards successful object manipulation. A grasp choice should also be based on a broader sense of context, such as object constraints and task constraints. Considering these factors allow us humans to grasp objects intelligently. For example, we grasp the handle of a mug if it contains hot coffee. We want to endow robots with the same capability, allowing them to select grasps that are functionally suitable for specific object manipulation tasks. And this problem is formally known as semantic grasping. Existing methods have learned semantic grasps in a data-driven manner, but they have primarily relied on low-level handcraft features or visual features. One example of such visual feature is the 3D shape descriptor FPFH extracted from the grasp region. As we can see from the figure, these low-level features have very large variance, therefore discovering structures in them is very hard, and has prevented methods that rely on them from generalizing to a wider range of objects and tasks. Other methods leverage more abstract semantic representations, such as object parts. However, they use them in terms of handwritten rules. For example, one rule is if the object is a spatula, if the task is to lift the object, then the robot should grasp the handle. We can clearly see that these handwritten rules are very hard to scale to a large set of objects and also tasks. We introduced ContextAware Grasping Engine, CAGE. CAGE uses a novel semantic representation that incorporates a more diverse set of contextual information for grasping than existing work. And instead of manually encoded rules, we use a neural network based on the wide and deep model to learn semantic grasps from data using the introduced semantic representations. Finally, to evaluate our method, we contribute a unique data set consisting of 14,000 grasps in different environmental contexts. In our task, we consider the context of a grasp as the label of the tasks that will be subsequently performed by the robot, a point cloud of the object, a spectral reading of the object from a SIO sensor, which is a portable spectrometer that can be used for material classification, and also a label specifying the state of the object. Here we make the simplifying assumption that the state of the object is given by the human user. However, this information can be also extracted from vision algorithms or using interactive perception or by reasoning, which we will show in the next project. In the following slides, we will use scooping with this empty spatula as a running example to discuss the novel semantic representations we develop and also the wide and deep neural network. Using RGBD image of the scene, we use an existing affordance detection method, AffordanceNet, to simultaneously classify the object and segment the object based on affordance. In this example, the spatula is segmented into the functional part with the support affordance and the handle part with the grasp affordance. Compared to other segmentation methods used by existing work, such as methods based on primitive shapes or heuristics, segmenting object based on affordance is more suitable to capture task-specific constraint on grasp regions. However, instead of directly using the detected affordance, we want to reason about them in the context. For example, even though the handle part of the spatula has the grasp affordance, grasping the functional part with the support affordance is actually more appropriate if we want to hand the spatula over to another person. Additionally, we see using visual affordance of object allow us to generalize among object instances and also classes. For example, in the bottom row shown here, the pen, spatula, and bowl all share the contain affordance. Come back to the system. Spectral readings of the object is used to classify the object material. Using material as a contextual information helps refine semantics of objects and also capture more complex reasoning patterns. For example, grasping the part of the knife with the cut affordance, which is the sharp part, is actually okay if the knife is made of plastic, because in that case, the knife won't damage the sensors on the grippers. We use an antipodal grasp sampler to sample stable grasps on objects. For each grasp, we assign the affordance and material of the object part closest to the grasp as the semantic representation of the grasp. In this case, the grasp affordance and grasp material are support and plastic, respectively. The values in these 6 color boxes that are extracted make up the semantic representation of the grasp and the object, which is denoted by X here. The wide and deep neural network is then used to collectively reason about these extracted semantic features. The neural network model PY given X, where Y is a class label indicating whether the grasp is suitable for the context or not. The wide and deep neural network was originally developed for recommender systems. We use them here because they balance between generalization and memorization, which we will discuss in detail next. The Y component of the network is responsible for memorization. Specifically, it captures complex reasoning patterns based on combinations of semantic features. For example, to avoid grasping contain part of a cup for pouring task, the network just needs to collectively reason about these 3 features, including contain, cup, and also pouring. The Y component achieved this ability by using one-hot encodings of features and a linear model. The deep component is responsible for unifying previous scene and new contexts. For example, this part of the network can help generalize avoiding grasps on an opening part of a bottle for the pouring tasks to scooping and handover tasks. It achieved this by using dense embedding vectors of features and multiple hidden layers to jointly reason about them. Using the wide and deep component together, the network is able to accurately predict the suitability of grasps in various situations. By iterating the prediction process, the system predicts a score for each grasp. Then the robot can execute the grasp with the highest score. For evaluation, we collected a large-scale semantic grasping dataset, SG14000. This dataset reflects diversity of environmental contexts that a robot will encounter in real life. We benchmark against 3 different baselines. CA ignores any contextual information and only considers grasp stability. VF grants semantic grasps to low-level visual features. FT considers a very simple relation between affordance of object parts and tasks by learning co-occurrence frequency between them. We use a standard metric, average precision, to evaluate ranked grasps. In the ContextAware Grasping evaluation task, we examine each method's ability to select suitable grasps for various contexts. The result shows that our method is able to outperform other baselines by statistical significant margins. Removing either the deep or the Y components in the ablation study shows that the performance will drop significantly. We also see that both the task and object state are crucial contextual information for robots to intelligently select semantic grasps. We also evaluate the effectiveness of our method on a fetch robot. The robot not only correctly predicted semantic suitability of all grasps, but were able to execute 15 out of 16 grasps that the system considers suitable. Shown here are some videos from the experiment. We see that the robot is able to grasp an object differently by considering the tasks. Other contextual information, such as the object state, also influence the selection of a suitable grasp. Semantic grasp can also be generalized between object instances within an object class and also between object classes, shown here. In summary, we show that to achieve semantic grasping, robots should reason about a broader sense of context, including task, object affordance, material, and state. We introduce a novel semantic representation of environmental context for grasping. Then we show how to reason about these semantic representation using a wide and deep model, which can capture complex reasoning patterns while maintaining generalization. So now we have talked about the benefit of modeling object properties. In this next project, we want to expand the set of object properties we consider and develop a framework that can model semantic relations between these object properties, particularly ones that can be grounded in multimodal perception. In recent years, many systems have been developed to ground semantic properties of objects in different sensor modalities, such as visual, auditory, and haptic modalities. However, a robot may not always be equipped with all the sensors, and the algorithms can be inaccurate sometimes. Therefore, it's important for the robot to be able to infer unknown properties from observed information. In the previous project, we assumed that the state of the object is given. In this project, we show that inference over the detected properties from multimodal perception allows the robot to infer the object state. Shown in the video here, the robot is using a material sensor and a temperature sensor to detect these properties. Then combined with properties extracted from vision and also localization, the robot can infer that the mug in the refrigerator is actually more likely to be full than empty. We would like to ask the question, what kind of semantic representation will enable this type of semantic reasoning? Prior work on semantic representations of object properties has primarily encoded pairwise relations between an object's class label and its properties, such as a cup is made of glass, a cup can be used for drinking, for example. However, a binary representation fails to take full advantage of multimodal observations because it ignores the complex relational structure between various object properties. For example, in a pairwise representation, observing that the cup is a cabinet does not help to infer whether the cup is clean or dirty. Our goal is to enable robots to collectively reason about object properties, particularly ones grounded in multimodal perception, and to predict semantic properties of objects based on partial observations. We introduce a novel semantic reasoning frameworks that uses unary relations to model complex interrelated object properties. This framework enables the ability to reason at different levels of abstraction. For example, a robot searching for a cup with no additional information is able to perform class-level inference to identify both the cabinet and sink as likely locations. Given additional information, such as that the cup is clean, an unary relation helps predict that clean cups are more commonly found in cabinet rather than in sink. A key challenge is to collect these semantically meaningful unary data. In other words, we want to know how often various object properties co-occur. Unlike binary relations, which can be created by experts or crowdsourced at scale, unary relations are very difficult to construct manually. Our solution is to learn unary relations from observations, each representing a set of identified semantic properties of an object instance within a particular environmental context. We use a multi-step crowdsourcing process to collect this instance-level data. The details can be found in the paper. We then introduce a transformer-based neural network to mine generalizable patterns from these instance-level observations. Our transformer takes as input embeddings of properties observed from an object instance and builds a contextualized embedding for the observed properties. The contextualized embedding is then used to predict unknown properties. To train our model, we randomly hide a single property from observed properties with a mask value and requires the model to reconstruct the hidden property. In this example, we require the model to reconstruct the location of this blue cup in the sink. Trained with this self-supervising objective on different properties and different object instances, The model will learn n-array relations and be queried to directly retrieve n-array knowledge or used to predict unknown properties of novel objects. To facilitate learning multimodal properties of objects, we contribute the semantically richest dataset to date, consisting of 1,457 object instances categorized into 11 object classes, modeled by 200 properties organized into 15 property types. We compare our method with 5 baselines on the dataset in predicting unknown properties of object instances. Compared to the top-performing baseline, a Markov logic network (MLN), our method shows significant improvement while reducing computation time by 150 times. At the heart of our model is the attention mechanism, which conditions each input property embedding on embeddings of other properties. Visualizing the attention weights show that our model discovers statistical patterns that strongly align with human intuitions. For example, cleanliness of an object is highly dependent on the dampness, location, and also whether the object is full or not. We validate our method in a real-world robotic tasks, where the robot needs to predict locations and rooms of objects based on a very sparse set of properties human users would normally provide. For example, find a clean glass cup or find a cold beverage. This experiment validates our model with a different set of users than the users who help construct the linked dataset. Compared to the baseline, our model is able to approach human performance at retrieving an object from users' top 3 locations within 2 tries or 3 tries. We also demonstrate the qualitative improvement. Equipped with our model, the robot is able to find objects considering different properties of objects. In this example, the robot searched for a dry sponge on kitchen counter and in the drawer, while tries to find a wet sponge in the sink. In summary, we show that semantic reasoning allows robot to predict multimodal properties of objects based only on partial observations. To achieve this task, we introduce a scalable transformer-based neural network that can model n-array relations between object properties. And the model is also able to perform inference at different levels of abstraction. Now I would like to turn back to Sonia for the next project.
Great, thanks, Weiyu. All right, so I'm going to talk about the third of our projects on semantic reasoning, this time talking about semantic reasoning for user interaction. Back at the very beginning when I defined the notion of semantic information, I talked about how semantics is an abstraction that often takes the form of word labels. We say the horse is pulling the carriage, or we say that this part of an object is a handle that's graspable. And so we're now taking low-level sensor data and abstracting it into a human-readable format. And here we're going to explore whether we can leverage these semantics in order to communicate with the robot's user. In particular, we're going to look at the scenario in which we have an autonomous system that is operating around humans, novice humans that are not robotics experts. And inevitably what's going to happen is that at some point this robot will fail. It'll stop working, it'll just stare at the environment usually, or beep, or something where it's not really performing the task that was intended. And naturally, what's going to happen to the user is that they're going to wonder, what happened? What was the cause of the failure? How do I avoid this failure in the future? And how do I fix the current problem? Should I reboot the robot? Should I move things around the environment? Should I push the robot out of the way? What should I do? And so ultimately, the research question behind this project is, how do we generate explanations? How does the robot generate explanations that can help non-experts understand robot failures and assist in failure recovery? Now, we've done a little bit of work on this topic before. We have a paper from HRI 2021 that explores the foundational part of this work. And what we found in that project is that explanations that provide context about the robot state and history of past actions are very effective for non-expert users. So if you are able to explain, hey, the robot's planning to pick up this blue can on the table, I drove up to the table, I segmented the scene, and I'm not able to reach it because maybe the can's too far away or the can is too close to these other objects. So that amount of context about what the robot can perceive and how it perceives it can be very helpful to users. In this particular work I'm going to talk about right now, The question is, how do we actually extract the needed semantic context in order to talk about it in the context of an explanation? How do we extract that context in a very generalizable way without making any assumptions about what objects are in the scene or whether we've seen this environment before? And the technique we're going to leverage, or the computational construct, is a semantic scene graph. I showed you an example of one at the very beginning with the horse and the carriage. And here we're going to take the same idea and apply it to the task of explaining a manipulation error. So here we have a robot that's failed a manipulation task. It uses the image from its camera to identify objects in the scene and learn the relationships or model the relationships between those objects. To construct this particular semantic scene graph, we're using the state-of-the-art MotifNet algorithm that we've adapted here to add a few relations that make a little bit more sense to our application, in particular occluding. So if one object is visible but it's significantly behind another one, we call that occluding. If things are too close together, we model that as well. And so we can customize this semantic scene graph to focus on relations that in particular are relevant to the types of failures we might encounter with manipulation tasks in a cluttered environment. And based on this type of graph, we can now generate what we call SSG explanations, semantic scene graph explanations, to the user. So here the task is again for the robot to pick up the can, and with the graph that I've shown so far, an example explanation would look like, oh, the robot couldn't pick up the can because it's on the table, occluded by the pitcher, occluding the bowl near the fruit and too close to the cups. Obviously this is not so good, right? We have too much information. The relevant information is in there, but it's diluted by all this other irrelevant stuff. And so we have a second part to our algorithm, which is to rank or filter the types of relations that we want to actually talk about. Here we're using a pairwise ranking algorithm that basically suppresses the edges that are not relevant to a particular explanation. And this is a computational model that's been trained and is generalizable to new scenes and is able to identify which edges are more likely to be important and others not. And so with this ranked method, which we call SSG-R for ranked, we can generalize or generate much more focused explanations. One that says, the robot couldn't pick up the can because it's occluded by the pitcher and too close to the cups. And this is quite cool because not only can we do this in a fully generalizable way, but we can do this for multiple potential errors. Like here we have two potential errors and the robot doesn't quite know whether it's because of the occlusion or the closeness of the objects. Both of those factors ought to be mentioned. We do this in the context of manipulation, but you can also see this being applied in navigation, right? Though I couldn't get to my goal because the chair's in the middle of the hallway or the chair's blocking the door. So this idea of using semantic scene graphs to model and understand the relationships between objects and how they relate to robot autonomy, I think is really exciting. To evaluate how well this works with users, we ran a user study. This was during the pandemic, so we ended up using a simulation for this work and to generate dozens and dozens of scenes with different objects and different scenarios, and also different failure types. Everything from a single failure, like the cell phone is under a heavy book, to attribute failures, like the pillow can't pick up the pillow because it's too large to pick up. And the pillow is an interesting example because it's not a relation between two objects. That's the problem, but basically the relation between the object and its attribute. We know that this particular robot can't pick up very large objects or very heavy objects and so on. And so we gathered dozens of these different scenes and we presented them to users on Amazon Turk. We used 93 different users. We asked them to perform two tasks. One is to identify the cause of the failure, what happened, and then how they would solve it, the solution to the failure. And the study was run in two parts. First, we did a pretest. We showed them each person 16 failure scenarios, different ones, with no explanations and asked them to figure out the failure and how to solve it. And then in the explanation stage, we showed them 16 new failure scenarios, now coupled with explanations of different types. And we used 6 different types of explanations, or 6 different study conditions here. The first one is actually none, so there were no explanations for what happens if you just keep showing people examples. Eventually they'll learn, right? but you're not explaining anything. This is basically what we do with today's robotic systems. CB stands for context-based explanations. This is our baseline based on prior work. And then the SSG and SSGR explanations that I already described to you, which are based on this automatically generated semantic scene graph. And then we also tested against a variant in which we hand-coded the semantic scene graph just to eliminate the performance of that graph from the evaluation of the explanations themselves. So SSG star and SSGR star represent this idealized performance where the semantic scene graph is perfect. We only have a small error in our graph, about 10% of edges. Actually, it's not that small, but even with that, we just wanted to see the comparison. All right, now so I'll show you the results, and again, we're showing the difference in performance between the pre-test when people didn't have any explanations and the explanation phase. And when you're showing them no explanations, none, between the two, people do get slightly better, but not by much, right? So seeing more examples helps, but they're not getting much better. CB is actually, the baseline is designed for a very different type of explanation and didn't help in this scenario either. Throwing lots of information at them, SSG and SSG star, not ranked, just all the edges being presented to people, improves the performance slightly, but really is still very overwhelming. And doing the ranked, very much more focused or filtered explanations in this case leads to much improved performance in terms of people's ability to identify what went wrong and how to fix it. By the way, the left side of the figure is what went wrong, or failure identification, on the right is solution identification. And so, the big takeaway that I have for this graph is that developing robotic systems that don't explain anything about what went wrong is a problem, right? We don't want to continue to do that because users will end up being very confused about what's happening. It's very helpful if we can find ways, increasing ways, to explain the inner workings of our systems and what went wrong when we're deploying them with real people. Semantic scene graphs seem to be one potential way to do this in a very generalizable way. All right. Big picture. We've talked a lot about different types of projects that we've covered. All of them have to do with semantics. I want to take a moment to tie them all together. More than anything, through this work, I've learned that rich semantic data really expands the envelope of robot capabilities. We can push to completely new reasoning types and be able to solve completely new problems through the addition of this semantic data. But bringing me to the second point is that there's a challenge of modeling that data at the right level of abstraction in order to facilitate generalization. Abstracting the data too much it leads to overgeneralization and inability to really tell specific instances apart. Not generalizing enough slows down learning and generalization in the first place. And so there's this big challenge of finding the right level of abstraction, either for every problem or for every task. And the more we can automate that process of figuring out the abstraction, the better. And last but not least, every time we work with semantics, we end up having a human readable format for our data. We're taking really low level sensor data, making it much more human readable by adding all these human readable labels. There's a huge opportunity here to make our systems less of a black box, much more interpretable, much more explainable, and we should take advantage of that and make our systems be more transparent. All right, so these works that we talked about are all recently published in ICRA, RSS, and IROS over the last year or two. I certainly encourage you to check out the publications. And as always, a huge thanks to our lab, and in particular, again, big thanks to Wei-Yu Liu and Devlina Das, who led all of this work. And thank you all for listening.